Hello, everyone. Welcome back. I'm Steve,
And I'm Scott.
and together we're Backyard Musings, broadcasting live Apple Valley, People's Republic of California.
Yeah, and we're talking about a couple of good ones today. This one is interesting.
It first had a tone of sustainability and climate people, and that, but I like it. It's spawning a new industry. That's what it's doing. I like it. A new sustainable method has been developed to break down keratins, transforming leftover wool and feathers into useful products. Every year, textile and meat processing operations generate billions of tons of feathers, wool, and hair. These materials are rich in keratin, the tough fibrous protein found in hair, skin, and nails. Converting this animal waste into useful goods, from wound dressings and eco-friendly textiles to health extracts, could benefit the environment and help build new sustainable industries. The research is published in Nature Communications on July 26, 2025, and is also featured in a Behind the Paper blog post. Would you like to know more?
Okay, so I don't want to offend anybody, but our Indian friends, right? The people that were here before we came,
First Nation,
right?
Yeah.
Indigenous people,
Lamanites.
some people call them. Yeah.
Some people call them Lamanites.
That was one of their deals, right? They waste not, want not, right? They used every part of whatever they used. If they killed an animal, they used everything
the skin, the bones,
the
meat.
and we've just become a landfill society, right? We buy something, we use it, it breaks, we throw it away, or we burn it.
Or your iPhone, for example, what's an iPhone 3, right? I mean, you've recycled it plenty of times.
It's not an iPhone 3.
Oh,
Come
it's
on.
not?
No, it's a little bit newer than.
Oh, okay.
Did they even make an iPhone 3? Anyway, but yeah, we just become a society of use it, abuse it, throw it out, and it ends up in a landfill or recycle.
It's probably because we're so rich. I mean, we've been blessed with,
Yeah, but that's just not
right.
I mean,
I know.
We should learn how. I remember when my mom's toaster would break, she would take it to a repair shop, and it used to make my dad mad because he would want to try to repair it, but we don't do that anymore. We don't fix stuff. We just anyway. I'm kind of getting off the topic. So, the bottleneck is protein upcycling. Breaking proteins into their components usually relies on corrosive chemicals used in large, polluting facilities, which keeps an affordable process out of reach. Researchers at the Harvard John A. Paulson School of Engineering and Applied Sciences, SEAS, SEAS, have identified fundamental chemistry that explains how proteins such as keratin denature in the presence of certain salt compounds. This insight could move protein recycling forward in a meaningful way. Lots of things.
I want to hear more.
Right? Yeah. Fingernails.
Hooves.
Yeah.
Uh-huh. Yeah. A team led by Kit Parker, the Tar Family Professor of Bioengineering and Applied Physics at SEAS, combined laboratory experiments with molecular simulations to clarify how salts trigger protein unfolding. We were talking about this in Native Americans, right? I bet you they figured this out long time ago.
Well, did they have
salts?
Did they have salt? Did they have that kind of stuff?
Yeah, I mean the Great Salt Lake, there's salt there.
Well, yeah, but not every indigenous group or Indian tribe was by the Great Salt Lake, but I guess they had access to it, right?
Yeah.
So other places.
They found that concentrated lithium bromide, a salt known to break apart keratin, acts in a surprising manner. Rather than binding directly to the proteins as conventional wisdom suggested, it alters the. Oh, that's what I thought.
I haven't reached the conventional level of wisdom yet, so.
It alters the structure of nearby water molecules, creating conditions that favor spontaneous unfolding, being unburdened by what has been.
Yeah, so salt, which has taken a bad rap over the last couple decades.
I love salt.
4 or 5 decades.
I just used salt yesterday.
Yeah, it used to be used for a lot of things, like preserving meat, right?
Yep.
They would coat meat in it, and it would just hang in the
cellar.
Preparing
hides, curing hides. Yeah.
And like you just said, seasoning food.
Seasoning.
This insight allowed the researchers to design a gentler, more sustainable keratin extraction process, separating the protein out of solution easily and without the need for harsh chemicals. Okay, we like that. Yeah. The process can also be reversed with the same salt mixture, enabling recovery and reuse of lithium bromide, denaturants.
Yeah, that is cool. Get the stuff back, extract it back out so you can reuse it. It's like a little circle. This is a new industry. First author Yi-Chong Wang, a graduate, Yi-Chong Wang Chong? No Chong.
No.
A graduate student in chemistry who works in Parker's group, said the research builds on the lab's long-standing interest in developing keratin biomaterials with shape memory for biomedical applications. Wow, like wound dressing and stuff. They had previously observed that keratin extracted from lithium bromide solvents can form thick, shapeable gels that readily separate from the surrounding solution and solidify almost immediately when placed back in water. While useful, they found the behavior odd, and they wanted to understand it better.
To dig deeper, the team turned to the lab of Professor Eugene Shankovich in the Department of Chemistry and Chemical Biology, whose expertise is in protein biophysics. Molecular dynamics simulations led by co-author Zhulang Liu allowed them to see that the lithium bromides were not working on the proteins at all, but rather on the water around them.
Huh.
I don't understand that process, but
it turns out lithium bromide ions cause water molecules to shift into two different populations. Normal water and water molecules become trapped by the salt ions. As the normal water volume decreases, the proteins start to unfold due to the thermodynamic shift in the environment. Rather than being directly ripped apart like in other denaturation methods, quote, making the water less like water allows the protein to unfold itself, Wang said. They had similar results by testing simpler proteins like fibronectin, pointing to a universal mechanism.
Better understanding and designing protein extraction methods that are less energy intensive and less polluting than conventional ones opens potential avenues for protein upcycling industries. In the Parker lab, using keratin as a substrate for tissue engineering is a major research thrust. Having a reliable, sustainable method to extract and reuse such products would bolster their efforts.
So that keratin bandage, whatever, that helps to heal the skin. Is that what we're reading right here?
I don't know.
Huh. What's more, the process could lay a path for a whole new biomaterials industry, turning a massive waste stream like hair or chicken feathers into low-cost recycled materials, possibly as an alternative for traditional plastics, for example. Awesome.
I would have to see this on a YouTube video, I guess.
Well, you're watching a YouTube video right now, Scott.
Yeah, no, I mean an actual process.
Okay.
Yeah, I'm at that point in my life where I got to see something before I understand it or believe it.
Thomas. Or even Scott Thomas. Doubting Thomas.
Oh.
I got to see it.
Okay. Yeah. I mean, not everything, but stuff like this, it just, it's way over my
sorcery. Right. All right, folks. Thanks for joining us. We'll see you this afternoon.
Take care, everyone. Thanks for listening.